We've all been there, glued to our screens as starships zoom across the galaxy. They traverse light years in the blink of an eye. Star Trek, Star Wars, Battlestar Galactica. They all tantalize us with the possibility of interstellar travel. Imagine zipping from Earth to a distant star system. Picture yourself having breakfast on a planet orbiting Proxima Centauri. The vastness of space becomes a playground, ripe for exploration. But is faster-than-light travel truly possible, or is it destined to remain in the realm of science fiction? The truth is, the laws of physics, as we understand them, present a significant hurdle. Einstein's theory of special relativity, a cornerstone of modern physics, tells us that nothing can travel faster than the speed of light. It's a cosmic speed limit. However, that doesn't mean we have to abandon our dreams of interstellar voyages just yet. Scientists and science fiction writers alike have long pondered ways to circumvent this cosmic speed limit. One such concept that has captured our imaginations is the warp drive. Imagine a flat sheet. This sheet represents the fabric of space-time. Now place a bowling ball in the center. You'll notice the sheet curves around the ball. This curvature, my friends, is gravity. Einstein's theory of general relativity tells us that massive objects warp the fabric of space-time. This warping is what we perceive as gravity. Now, imagine creating your own gravity well in front of your spaceship. This well would cause the space-time in front of you to contract, pulling you forward. At the same time, you would expand space-time behind you, pushing you further along. This, in essence, is the concept of a warp drive, manipulating the very fabric of the universe to achieve faster-than-light travel. To truly grasp the mind-boggling concept of warp drives, we need to delve a little deeper into Einstein's universe. Einstein's theory of general relativity, published in 1915, revolutionized our understanding of gravity. It wasn't simply a force acting at a distance, as Newton had proposed. Instead, gravity was a consequence of the curvature of space-time. Imagine space-time as a giant rubber sheet. Massive objects, like stars and planets, create depressions in this sheet. Smaller objects, like our spaceship, then follow the curves of these depressions, resulting in what we perceive as gravity. This groundbreaking theory provided the foundation for understanding the evolution of the universe, the behavior of black holes, and even the possibility of warp drives. In 1994, a Mexican physicist named Miguel Alcubierre proposed a theoretical model for a warp drive that sent ripples through the scientific community. Alcubierre's solution to Einstein's equations suggested that it might be possible to create a warp bubble. This bubble would compress space-time in front of a spacecraft and expand it behind, effectively allowing the craft to ride a wave of distorted space-time. Imagine a surfer riding a wave. The surfer doesn't move through the water so much as he is carried along by the wave itself. Similarly, a spacecraft inside an Alcubierre warp bubble wouldn't technically exceed the speed of light. Instead, it would be propelled by the distortion of space-time itself. Alcubierre's warp drive, while theoretically sound, faces a rather significant hurdle: energy. The amount of energy required to create an Alcubierre warp bubble is astronomical, to say the least. We're talking about energy on a scale that dwarfs the total energy output of our Sun. In the early days of warp drive theory, it was believed that creating such a bubble would require more energy than the entire observable universe contains. However, recent research has offered a glimmer of hope. Some physicists believe that by manipulating the shape of the warp bubble, the energy requirements could be significantly reduced. We're still talking about enormous amounts of energy, mind you, but it's a step in the right direction. While warp drives aim to distort space-time to achieve faster-than-light travel, wormholes offer a different approach: shortcuts. Imagine folding a piece of paper in half so that two distant points touch. A wormhole, theoretically, would function in a similar way, connecting two distant points in space-time through a tunnel-like structure. These cosmic shortcuts, predicted by Einstein's equations, could potentially allow us to travel vast distances in a fraction of the time it would take to traverse normal space-time. Step into one end of a wormhole, and you could emerge light years away, on the other side of the galaxy. It's a tantalizing concept, but like warp drives, wormholes come with their own set of challenges.